The first chapter of Unit 7, that is the unit of modern physics, consists of photoelectric effects, and here we will study about photoelectric emission. We will study the deduction of the photoelectric equation, and we will also study some applications of photoemission. So we know that the electrons in the outermost shell of an atom are loosely bound and they are called the free electrons. Mane electrons jibur outermost shell or thake eta atom or he hote loosely bound hoy thake and they are called the free electrons. And the minimum amount of energy which is required by an electron to just escape from the metal surface is known as the work function of the metal. Mane jiman khini minimum energy he electron he free electron tuk lage to just so that it can just escape from the metal he ulai jabo pare from the atom of the metal is known as the work function. The work function is denoted by W naught or phi naught, and it depends on the nature of the metal. That is, different metals have different work functions. প্রত্যেকটো বেলেগ বেলেগ মেটেলৰ work function to বেলেগ বেলেগ থাকে, and it is denoted with the SI unit of electron volt. Okay, the emission of electrons from metal surface is known as electron emission, and there are various methods which are used for electron emission, like suppose thermionic emission, field emission, secondary emission, and photoelectric emission. But here we will only study what is photoelectric emission. So photoelectric emission is the process of emission of electrons because of or due to the irradiation of the surface of the metal by electromagnetic radiation of sufficiently high frequency or energy, and the emitted electrons are called photoelectrons. Mane ki hoy, suppose this is a metal, this one is the bound electron inside the metal, and this one I have provided an incident photon or an incident light with sufficient energy. Their energy to sufficient enough hobo lagibo so that it can make this bound electron move away or escape away from the atoms, from the atom in or from the metal surface. And a bound electron to jetia gusi jabo, it will escape away. It will escape away as a photoelectron with a kinetic energy of half mv square, and this whole process is called photoelectric emission or photoelectric effect. Okay, and there is a equation which is known as the Einstein's photoelectric equation, which is related to this whole process. So Albert Einstein, he explained the photoelectric effect by using Planck's quantum theory of radiation and the law of conservation of energy. So the incident energy, which is E is equal to h mu, is here used for two purposes. Mane is the incident energy to ami provide korisu etu duta kamor karone use hoy. The number one purpose or the prothom to kam to hol to liberate the electron from the nuclear attraction. Mane is a bound electron jintu bound hoy ase nijor nuclei to logot nijor atom to logot hey electron to uliai pathabole jiman kini minimum energy lage ekhini ei incident radiation to ba incident photon to tak die. Mane hetu ki hoy, hetu ki hoy, the work function to hoy, and this denoted by W naught is equal to h mu naught, or you can just replace frequency by c by lambda, and here W naught is the threshold energy, lambda naught is the threshold wavelength, and mu naught is here the threshold frequency. Okay, this one is the first thing. The second purpose is to provide maximum kinetic energy to the ejected electron. Mane is a bound electron to ase that enough kinetic energy dibo libo so that it can eject away as a photoelectron, and that maximum kinetic energy is denoted by half mv max whole square, which is Vmax is the maximum velocity which can be gained by the photoelectron. So now from the law of conservation of energy, what we can write is h mu is equal to W naught plus kmax. Mane ki h mu is the energy we have provided, the incident energy, which is used in two work. Number one is to give it the work function to liberate the electron from the nuclear attraction. Number two is the give it the energy so that it can move away, right? So h mu is equal to h mu naught plus kmax is half mv max square. You can just take the term here in the left hand side and take this two term here so that you can get the photoelectric equation, or you can also state it as an Einstein's photoelectric equation. There are four laws regarding the photoelectric emission. The number one law is the rate of emission, which states that the number of photoelectrons which are emitted from the metal surface per second is proportional to the intensity of the incident radiation at a given frequency. Mane, the more will be the intensity of the incident radiation, we will get more number of photoelectrons emitted from the metal. The second is the law of maximum kinetic energy, which states that above the threshold frequency, the maximum kinetic energy of the emitted photoelectrons is directly proportional to the frequency of the incident radiation. Number third law is the threshold frequency, which we already know that there is a certain minimum frequency of the incident radiation, which is known as the threshold frequency, below which no photoelectron is emitted. Mane jetialeke threshold frequency incident radiation to nohoge tetialeke ami photoelectrons napao. Number four, the last law is the law of time lag. The photoelectric emission is an instantaneous process. There is no detectable time lag between the irradiation of an emitter and the ejection of the photoelectrons. Mane jetia amar incident radiation to metal surface of ami pelao and next jetia photoelectron ta eject ho ulai jay tar majot eku detectable time difference nai, mane gute process to instantaneous process hoy. So now coming towards the applications of photoemission. The first one is here you can see a photoelectric cell. A photoelectric cell or a photocell converts a change of intensity of radiation into a change in photocurrent. That is, in the output we get a current, a photocurrent, which is known as photocurrent. But this photoelectric current is very low in measurement, because you can see here the emitter is measuring in microampere. So the current is very low, and to be practically applied somewhere we need to amplify the current before using it. And there are also other various applications of photoemission, like it is used in cinematography for reproduction of sound. It is also used in counting devices. It is used in various alarms like burglar alarm and fire alarm. It is used in photographic cameras. Photoemission is also used in control of street light system, in automatic control system, and it is also used in meteorology for recording of day temperature. So now let us see a numerical related to photoelectric emission. The question is, if the work function, that is W naught for sodium, is 2 electron volt, can light of wavelength 6800 Armstrong eject photoelectrons from the surface of sodium? You have been given the Planck's constant, which is equal to 6.7 into 10 to the power minus 34 joule second. The question is asking that ki hudise dia ase the work function of sodium is 2 electron volt, hetu ami jano. So we are provided a light of wavelength 6800 Armstrong. So can that light eject photoelectrons? Mane he light to e photoelectric emission to khotabo paibon nai, hetu hudise. So okay, so first of all we have to find out the energy of the incident radiation, right? So we are given wavelength. So we are not given frequency, we have been given wavelength. So we need to write h mu holoni ami h c by lambda likhibo lagibo, because we know the lambda here. So h value ami jano, yet put kora. C value you know 3 into 10 to the power 8, and lambda value is given 6800 Armstrong. You need to convert the Armstrong to meter. 6800 into 10 to the power minus 10 meter, because 1 Armstrong is 10 to the power minus 10 meter. So calculate it and you will find the energy of the photon in joule. So now you need to find out the work function for sodium, which is given as 2 electron volt. 2 electron volt means electron volt eta joule le convert korile ami into koribo lage with 1 electron charge, which is 1.6 into 10 to the power minus 19. So you get 3.2 into 10 to the power minus 19 joules. So clearly the energy is less than the work function, right? So energy, incident energy to the work function of the metal ke less hoy, then it cannot eject electrons. That is, it cannot undergo it cannot create the photoelectric emission. So you will write that there will be no ejection of any kind of electrons. The second chapter of Unit 7 is nuclear energy. So here we will learn what is a nucleus, what are the constituents of a nucleus, and also we will learn what is nuclear energy. So, a scientist named Rutherford in 1911, he postulated from his experimental observations about the existence of nucleus inside an atom. And according to Rutherford, the entire positive charge and most of the mass of the atom is concentrated in a small volume, which is known as the nucleus, and a suitable number of electrons revolve around it. So, Rutherford amak ki kole that the entire positive charge of an atom, jitu positive charge ase, and plus the almost all the mass of the atom, atom to almost mass at a volume that concentrated in the volume to nucleus boliko. And also from Rutherford's experiment, it was found that the nuclear size is of the order of 10 to the power minus 14 meter. What is the size of the nucleus? Around 10 to the power minus 14 meter. And it was also found out that the nucleus and the diameter of the atom is of the order of 10 to the power 10 meter. So diameter of the atom, atom eta diameter to almost 10 to the power 10 meter. So what we can conclude is that the most of the atom is empty. Okay, and also we know that the electrons revolve around the heavy nucleus, where positive charges on the nucleus equals the total negative charge of the electrons. আমি already জানো যে electrons which are negatively charged, they moves around the nucleus of an atom, right? And the here is the positive charge, যিমানখিনি positive charge থাকে nucleus থাকে, and it equalizes with the electrons negative charge, equal হৈ থাকে with the electrons negative charge. Okay, so protons and neutrons are the constituents of a nucleus. Nucleus etar bhitorot ki thake? Protons and neutrons thake. But protons and neutrons are together called as nucleons. So you can also state that nucleons are the constituents of a nucleus. So proton was discovered by Rutherford himself, and neutron was discovered by a scientist named Chadwick in 1932. Protons and neutrons are the main building block of a nuclei of all the atoms. Protons are positively charged particles, which you already know, and they give the positive charge to the nucleus. It is a fundamental particle which can be also stated as the nucleus of a hydrogen atom. And neutron are chargeless particles. You know that already, neutron or charge nathake, and its mass is slightly greater than that of a proton. Mane protonotke neutronor mass to slightly besi thake. Okay, so protons and neutrons together gives the mass of the nucleus, and protons and neutrons are identical particles in the sense that their masses are nearly the same. Okay, so these four terms you have to know the definitions of these four terms. So first one is the atomic number. So atomic number is the number of protons inside a nucleus. Okay, nucleus etar bhitorot kimanta protons ase hetuke ki boli koa hoy? Atomic number boli koa hoy, and it is denoted by the capital letter Z. Okay, the next thing is mass number. Mass number is the total number of protons and neutrons which is present inside the nucleus. Mass number mane protons plus neutrons. Eta nucleus or bhitorot kimankhini proton plus neutron ase hetuke koa hoy mass number boli, and it is denoted by the capital letter A. The next is nuclear mass. Nuclear mass is the total mass of the protons and neutrons which is present inside a nucleus. Gutekhini mass mane total mass of proton plus neutron is called the nuclear mass. Okay, and the next thing is, last thing is nuclide. Nuclide is a specific nucleus of an atom which is characterized by its atomic number Z and the mass number A. Mane jikono eta suppose tumi atom loisa, tar specific nucleus eta ase, aru hei nucleus tuk tumi jodi likhibo goisa, denote koribo goisa, describe koribo goisa with its alongside with its atomic and mass number, then you will write it like this. It is denoted, a nuclide is denoted like this. Okay, here X is the chemical symbol of the element. Jitu element tumi loisa hetu denote kora tumi X hisabe, and Z is the atomic number. As you already know, Z, you write it here, Z is the atomic number, and the mass number is written there. Okay, so a nucleus is not a solid body. Its boundary is not well defined, but we assume that the nucleus is spherical in shape, and if R is the radius of a nucleus of an element which has a mass number of A, then the radius of the nucleus is given as R is equal to R naught A to the power 1 by 3, where R is the radius of the nucleus, R naught is a constant, and A is the mass number of that specific element. Okay, and R naught is a constant which value is approximately 1.2 into 10 to the power minus 15 meter, which is equal to 1.2 femtometer. FM is femtometer, which and you have to remember this, it will please monot rakhiba, 10 to the power minus 15 meter is equal to 1 femtometer, and femtometer is a unit which is usually used in any kind of nuclear measurements. The next thing is nuclear density, and the nuclear mass density is found out to be of the order of 10 to the power 17 kg per meter cube, which is a very large number as compared to the density of ordinary substances. And the thing to be noted here is that the nuclear density is always independent of the size of the nucleus. Next is atomic mass unit. All the nuclear measurements are done in terms of a unit which is known as the atomic mass unit, and one atomic mass unit is defined as 1/12 of the mass of carbon 12 atom with mass number 12, and the mass of one carbon 12 atom is equal to 1.99 into 10 to the power minus 26 kg, and hence 1 AMU is equal to 1/12 of one atom of carbon 12, right? So 1 AMU is found out to be 1.66 into 10 to the power minus 27 kg. So some of the known masses which are expressed in terms of atomic mass unit are given here. Number one is the mass of an electron, which is equal to 0.00055 atomic mass unit, which is equal to 9.11 into 10 to the power minus 31 kg. The mass of a proton is equal to 1.0073 atomic mass unit, which is equal to 1.67 into 10 to the power minus 27 in kilogram. The mass of a neutron is almost equal to mass of a proton, which is equal to 1.0086 atomic mass unit, which is again equal to 1.6749 into 10 to the power minus 27 in kilogram. So if you're asked what is the mass of a hydrogen atom, jodi tumak khudhe eta hydrogen atom or mass kiman, so you have to know that the mass of hydrogen atom is equal to the mass of one proton plus mass of one electron, because one hydrogen atom is made up of one proton and one electron. So it is equal to the mass of one proton plus mass of one electron, which gives us it's equal to 1.0078 atomic mass unit. And there is a relationship between electron volt and atomic mass unit, which is expressed as 1 AMU is equal to 931 into 10 to the power 6 electron volt, which you can also write as 931 mega electron volt, because 1 mega electron volt is equal to 10 to the power 6 electron volt. Mass and energy are convertible into each other. That is, mass can be converted into energy and energy can be converted into mass. And the equivalence between mass and energy is given by the Einstein's famous equations, or equation of equivalence of mass and energy, which is E is equal to mc square, where E denotes energy, m is the rest mass of any particle, and c is the speed of light. So it is found that the mass of a stable nucleus is always less than the sum of the masses of its constituents, protons and neutrons in their free state. Mane, if this one is a combined nucleus, mane suppose this is a nucleus, and these are the protons and neutrons which are inside that nucleus. Nucleus or bitorat apni jano je ki thake neutrons and protons thake. So this neutrons and protons, suppose here 8 neutron and proton mili eta nucleus hoise. So if you measure the mass of that nucleus separately, and if you take all the constituents separately, individual particles hisabe tumi loisa, and then you measure the mass of those individual particles, then you will find that hobo lagisil ki the constituents and the combined nucleus should have the same mass, but it doesn't happen. So what happens is the individual particle mass is always greater than the mass of the nucleus. So here m is the mass of the individual particles, m dash is the mass of the nucleus. So here what happens, m is always greater than m dash, and this difference between the rest mass of a nucleus and the sum of the rest masses of its individual constituent nucleons is known as the mass defect, which is denoted here by delta m. So delta m is equal to m minus m dash, which is known as mass defect. Next is a definition which is called packing fraction. So packing fraction is the mass defect per nucleon. Okay, so if you divide this mass defect delta m by the mass number, that is or by per nucleon A, then you get delta m by A, which is known as packing fraction. So the next topic is binding energy. So here I will first take two cases. Suppose number one case is, suppose you need to take some individual particles, that is protons and neutrons, and you need to fuse them together to form a nucleus. To be individual particles kitaman loisa protons and neutrons, tumak moi ekita disu to fuse them together to make it a nucleus. Okay, the second case is you take a bigger nucleus and you need to break that heavy nuclei to make it into some smaller parts. Mane tumi nucleus to loisa, and you need to break that nucleus to convert them into their individual particles, mane protons and neutrons. Okay, so in the first case, what happens when a nucleus is formed from individual protons and neutrons, then a certain amount of mass disappears, which is converted into energy, and that certain amount of mass is nothing but the mass defect that we studied earlier. Okay, hey mass defect ki kore energy le convert hoy aru he energy kini release hoy in this first case. And in the second case, what happens, because the nuclear forces are attractive in nature, so energy is required to break that nucleus into its constituent nucleons. Mane because these protons and neutrons are sitting inside the nucleus with some attractive force, so you need to provide energy to me energy so that they you can break the attractive force between the nucleons, and the nucleus is broken into its individual particles. Okay, so from these two cases you can give the definition of binding energy. So the energy which is required to break the nucleus, or the energy which disappears in the formation of the nucleus from its constituents, is known as the binding energy. And you can also define binding energy as the energy required to break up a nucleus into its constituent protons and neutrons, and to separate those protons and neutrons to such a large distance that they may not interact with each other. Mane ইমানখিনি distance হলে আমি এটা কটৰাই পঠাব লাগিব, so that they remain as individual particles and does not cannot form the nucleus again by the attractive forces between them. So here the graph you are seeing here is the binding energy graph. The x-axis is the mass number A, and the y-axis is the binding energy per nucleon, which is given in mega electron volts. So if you see the graph, here are these are all the nuclei. Okay, so if you can break this graph into mainly three parts. So this one is suppose this one is the first part, where you can see the binding energy per nucleon is increasing slightly as the mass number is increasing. So this one is the second part, where you can see the binding energy is almost constant, almost ek ase from here to here. Okay, and in the third region you can see that the binding energy is slightly decreasing from this constant term. Ekhini jimankhini constant asile tar pisot hi laheke decrease hol. So these three terms, these three regions suggest you three different things. Okay, ইয়াৰ ভিতৰত part 1 ৰ ভিতৰত যিমানখিনি নিউক্লিয়াই আছে, হেবোৰ নিউক্লিয়াই, those nuclei are prone to fusion. মানে fusion মানে কি হয়? Fusion is two smaller nuclei which fuses together to form a large nucleus, because these are small nuclei, right? Small nuclei because their mass number is small, তলত আছে, সৰু হয়. So this small nuclei together fuses together to form a large nuclei, that is called fusion. And these nuclei in the first part, in the first region, are prone to fusion. Mane ihoti fusion fusion jetia hoy ebu nuclei mazot hoy. Okay, the second part is this one. The second part is this one. So this region is important because here the binding energy per nucleon is almost the constant, almost same. And this iron 56 iron, মানে iron jitur atomic mass 56 hoy, this is the nuclei which has the highest binding energy per nucleon. And this constant term is around 8.6 mega electron volt. Okay, so this nuclei in this range are the most stable nuclei. Why? Because they have the maximum binding energy per nucleon. Maximum binding energy per nucleon mane ki hoy, hiyotor major jibur protons neutrons ase, ebu nuclei bhitorot jibur protons neutrons ase, hihoti more attractive force of nucleus or major bohi ase, and you need to provide much more energy to break them, to break those nucleus. Mane most stable nuclei mane ki hiyotok ami bhangibole, these nuclei you need to give much more energy. Ekita nuclei bhangibole tumi jiman energy dibo libo, tatke bahut beshi energy tumi ekita nuclei bhangibole dibo libo. So these nuclei are the most stable nuclei in nature. Okay, coming to part 3, in the region 3 what happens? These nuclei are in the range of more than 200, mass number 200 or par ho gese, mane ki hote heavy hoy, they are heavy. These nuclei are heavy in nature, and heavy nuclei ki hoy, they are prone to fission. What is fission? Fission is a heavy nucleus which is splitting up into two smaller nuclei, liberating a large amount of energy. Suppose in case of atom bomb ki hoy, dangor eta nuclei which is very unstable, that is it gets splits up into smaller particles, and in that process a large amount of energy is released, right? So these nuclei are prone to fission. Let us now see a numerical related to nuclear density. So the question is, the nuclear mass of iron 56 is 55.85 atomic mass unit. So you need to calculate its nuclear density. What is given is the R0 value, which is 1.1 femtometer. First convert this R0 into meter. It will be 1.1 into 10 to the power minus 15 meter. So first you are given the mass of iron. Okay, the mass of iron is 55.85 atomic mass unit. Convert it into kg. You have to multiply it with 1.66 into 10 to the power minus 27 kg. So you get 9.27 into 10 to the power minus 26 kg. You will always have to convert AMU into kg. Then the nuclear, find out the nuclear radius, because you are given R naught and atomic mass. You know the atomic mass, so you can calculate the radius, which is R is equal to R naught A by a to the power 1 by 3. So R naught value is 1.1 femtometer. To take it into meter, you have multiplied by 10 to the power minus 15, and the atomic mass is 56, right? So 56 to the power 1 by 3. So you have been asked to find the nuclear density. So what is nuclear density? Nuclear density is denoted by rho, and density is always equal to mass per unit volume. So the mass of the nucleus is already known, right? So MFE will be this value. Then the volume is 4 by 3 pi r cube. You know the value of r, you have calculated r from here. So please calculate this value, okay? Multiply this and calculate the value of r, and 4 by 3 pi value you know, put the value of r here, r cube, and you will get the nuclear density, the unit of which will be kg per meter cube. The next chapter is radioactivity. The substances which spontaneously emits penetrating radiations are called radioactive substances. For example, all those naturally occurring elements which has the atomic number greater than 82, they shows radioactivity. For example, uranium, polonium, radium, thorium, etc. And this phenomenon of spontaneous emission of radiation by radioactive substances is what is known as radioactivity. Radioactivity is the spontaneous disintegration of a nucleus of one or more atoms. So in radioactivity, the radiations which are emitted, they are known as radioactive radiations. Radioactive radiations can be alpha rays, or can be beta rays, or can be gamma rays. So next is the units of radioactivity. There are mainly 3 units of radioactivity. Number 1 is the unit of becquerel, the SI, which is the SI unit of radioactivity, and 1 becquerel is equal to 1 decay. It is defined as 1 decay per second. The next unit is Curie, which is the symbol of Curie is Ci, and 1 Curie is equal to 3.7 into 10 to the power 10 decays per second. That is, 1 Curie is equal to 3.7 into 10 to the power 10 becquerel. And the third is the unit of Rutherford, which is written as small rd, and 1 Rutherford is the decay rate of 10 to the power 6 disintegration per second, which is again equal to 10 to the power 6 becquerel. So here is a comparative study of the properties of radioactive radiations, that is the alpha rays and the beta rays and the gamma rays. You can see the differences here between the alpha rays, beta rays and gamma rays. So first of all, let us see what is an alpha ray. So alpha rays are positively charged particles, and these particles are nothing but the helium nuclei itself. You can see here helium nuclei is denoted as 2He4. So 2He4 is known as the alpha particle, and the radiations which consist of this alpha particle are called the alpha rays. So they are positively charged rays, and they have a charge of plus 2e. You know that 1e is, you can write 1e as 1.6 into 10 to the power minus 19 coulomb. So plus 2e will be what? 1.6 into 2, right? That's 3.2 into 10 to the power minus 19 coulomb is the charge of the alpha particles. So they have the minimum penetrating power, that is the power with which it can penetrate any object or a surface. They have the minimum in case like when you compare it with beta or gamma radiation, the alpha radiation has the minimum penetrating power. The mass of one alpha particle is denoted here, given as the mass of one particle, alpha particle, is estimated to be 6.67 into 10 to the power minus 27 kg, and their velocity of one alpha particle of the alpha particles is around 10 to the power 7 meter per second. Okay, so next is the beta radiations. So the beta particles are the fast moving electrons of nuclear origin, and they have the charge. You can see their electrons or positrons. Electrons are negatively charged, so E minus, and positrons are positively charged, so E plus, and the charge is always minus E. So the charge is minus 1.6 into 10 to the power minus 19 coulomb, and the penetrating power of beta radiations is 100 times more than the alpha radiations. The mass is estimated to be around 9.11 into 10 to the power minus 31 kg, and the velocity of beta particles is around 10 to the power 8 meter per second. Okay, so the third is gamma radiations. So gamma radiations are just electromagnetic waves which have the wavelength even lesser than the x-rays, and they shows all the optical properties like reflection, refraction, etc. And they are, these gamma rays are not like, they are not affected by any electric or magnetic fields. So which tells us what? So they have no charge. These radiations are chargeless, so hence they are not affected by any kind of magnetic or electric field. And the penetrating power of gamma rays is 10 to the power 4 times as that of alpha rays. So they have the gamma rays have the most penetrating power, and the rest mass of gamma rays or the gamma particles is zero, and the velocity of gamma particles are around 3 into 10 to the power 8 meter per second, which is equal to the velocity of light. Radioactivity can be of two types. Number one is natural radioactivity. Number two is induced or artificial radioactivity. So natural radioactivity, যেটো আমি নামতে গম পাওঁ, it occurs naturally. Any element in nature which undergoes radioactivity naturally যেটো process হয়, আমি তাত একো induce কৰা নাই বা আমি একো help কৰা নাই, naturally spontaneously যেটো হৈ আছে radioactivity, হেতুকে কোৱা হয় natural radioactivity. And suppose here A is a radioactive nucleus. I am showing here a series of decays according to which the radioactivity occurs. Suppose there is an alpha emission, this nucleus decays into A1, then A1 undergoes a beta emission, then it converts into, gets into A2, then there is again one alpha emission, it spontaneously goes decay in this process. Okay, this one is natural radioactivity. Number two is induced or artificial radioactivity. Etu namote gom poa jay, it is artificial, it is done in laboratory, it is man-made. Ami etu bostu koru because it is also possible to make an element unstable, okay, by artificial means, so that it breaks up and it starts emitting some kind of radiation, and this type of radioactivity is called artificial radioactivity. So what happens in this process, what happens, the nucleus is bombarded with some kind of radiation. Okay, jitu nucleus ami bisaru ki radioactivity process to start korok, then we bombard that nucleus with some kind of radiation. Then the particle which constitutes the incident radiation, the particle মানে যিটো ৰেডিয়েশ্যন আমি পঠাম, সেই ৰেডিয়েশ্যনটোৰ কাইনেটিক এনাৰ্জিটো সিমানখিনি হ'ব লাগিব, so that it can penetrate into the nucleus. Okay, so when it enters the target nucleus, then a compound nucleus is formed which is unstable. যেতিয়া সেই ৰেডিয়েশ্যনটোৱে সেই নিউক্লিয়াছটোক হিট কৰিব, then there is formation of a compound nucleus which is unstable, and unstable হলে কি হ'ব, unstable হলে সেই বস্তুটো decay হ'ব চাব, so that it reaches stability. So the compound nucleus, it then breaks up to produce a nucleus by emitting a radiation. This whole process is induced or artificial radioactivity. So here is an example of induced or artificial radioactivity. Here nitrogen, you can see here nitrogen getting bombarded with alpha particle helium, and it produces a compound nucleus fluorine. So fluorine here is radioactive, so radioactive fluorine needs to decay so that it can reach stability. So fluorine decomposes or decays into oxygen, producing one hydrogen, and mu is here the energy evolved, and this one is the one example of artificial radioactivity. So there are various applications of radioactivity or radioactive radiations. You can search for yourselves. There are many applications. Here I have just provided just very few applications. So number one is radiocarbon dating. So carbon dating is a process which is used by archaeologists and paleontologists to determine the age of any kind of ancient sample, to determine its age, like from which era does it belong, and what is the age of that particular sample. Okay, so the next is it is used in medicine. So this is the most used area of radioactive radiations. It is used in diagnosis and therapy. You already know that radioactive isotopes are used to determine the to determine the location of cancer patients. It is used in case of cancer patients. It is used to determine the condition of human thyroid gland. It is also used to locate hemorrhage within a body or the human brain. So it is basically used in all diagnosis and therapy in medical field. And radioactivity is also used in agriculture for large scale food preservation, for like there are isotopes which emits gamma rays which can destroy bacteria, to offer complete sterilization of foods, and basically to get the optimum soil conditions which is necessary for agriculture. So suppose let us assume that there is an atom in the ground energy state E1, and suppose I am providing a photon of energy h mu. The energy of the photon is h mu, and the photon and this atom absorbs this photon and gets excited, and that is it jumps into its excited state E2, energy level E2. But for this to happen, for this phenomena to happen, there has to be a condition which needs to be fulfilled, which is given here as E2 minus E1 is should be equal to h mu. That is the photon energy h mu. Here you can write the photon energy is equal to h mu should be equal to the, and it should be equal to the energy difference between the two states, that is the E2 minus E1, that is the energy difference between the higher excited state and the lower ground energy level should be equal to the energy of the incident photon. And this whole process is called induced absorption or stimulated absorption. Because why? We have induced the absorption. Induced মানে আমি বাহিৰৰ পৰা কিবা এটা দিছো, আমি induced কৰিছো, বাহিৰৰ পৰা আমি নিজাকে এটা photon দিছো, so that this atom absorbs that photon and gets excited to its higher energy state. Okay, so generally what happens is the number of particles in the ground state are much more than the number of particles in the excited state, because the time for which a particle can exist in the ground state is unlimited. A particle, এটা atom বা এটা ion বা এটা molecule, এটা ground state সিহঁতে unlimited time কাৰণে থাকিব পাৰে, but that is not so in case of any excited state. In the excited state they can remain for a limited time. There is only a limited time for any particular excited energy state for which the atom or the molecule can sustain there, and that amount of time is known as the lifetime of that particular excited state. So generally the lifetime of any excited state is order of 10 to the power minus 8 second, but there are some excited state in which the lifetime is greater than 10 to the power minus 8 seconds, and those states are known as metastable states. So after the induced absorption or the stimulated absorption, মানে যেতিয়া এটা atom stimulated absorption or সহায়ত excited state এটালে গ'ল, and because we have learned that what excited state এটা atom বা molecule এটা সদায় কাৰণে থাকি যাব নোৱাৰে, it has to come to the ground state, it has to emit the radiation and come to the ground state. So because it cannot stay longer in the excited state, it has to return to the ground state by emitting a photon of frequency mu, that is energy h mu. And this emission can occur through two process. One can be, it can either occur through spontaneous emission or it can occur through stimulated radiation. So let us see what are these two process of emission. So first one is spontaneous emission. So when a particle jumps from a higher excited state to the lower excited state by spontaneously emitting a photon of energy h mu, it spontaneously মানে naturally হি এৰি দিয়ে energy to lole h mu, induced absorption সহায়ত হি কি কৰিলে lower পৰা upper energy state হলে higher energy state লৈ গ'ল, and after staying for that lifetime, যেটো lifetime age energy state to হয় ইমানখিনি time হি তাত থাকিলে, and after that it spontaneously comes down to the lower energy state by emitting a photon of energy h mu. Then the transition is said to be spontaneous emission. And you can see the figure here. This is the figure of spontaneous emission. It is random in nature. So if there is a group of atoms, here I have shown only one atom, right? So if there is a group of atoms, then the radiation which will be emitted spontaneously by every individual atom will have random direction and random phase and random amplitude, right? So therefore the radiation is a random mixture of many quantums which have various wavelengths. So these waves do not have the same wavelength and phase, so this radiation is incoherent and it has a broad spectrum. So the next one is stimulated emission. So stimulated emission is a forced emission. This does not occur naturally. It is a forced emission. We induce something so that this emission happens. So what happens here is there is an interaction between the excited atom and the photon which can trigger the excited atom to make a transition to the ground state. মানে আমি induce কৰিছো এটা photon of energy h mu so that this excited atom gets triggered to get down to its lower energy level. Okay, এই যে lower এই h mu টো যোনটো আমি induce কৰিছিলো হেতু ওলাই যাব আৰু তাৰ লগতে যেতিয়া এই atomটো excited atomটো তললৈ আহিব ground state লৈ আহিব, then also it will release the same h mu photon. So this there will be emission of 2 h mu. Remember that in spontaneous emission there will be only the emission will have h mu, only one photon, but here it will be 2 h mu because it will have two photon. The transition will generate also a second photon and it will be identical to the triggering photon with respect to the energy, phase, direction, amplitude. মানে কি coherent hobo এইটো process coherent নহয়. Coherent মানে when two waves are two waves when two waves are traveling with the same amplitude, same frequency, same phase difference, same phase angle, same energy, etc. When they have the same properties, then they are said to be coherent. Okay, and in this process, this whole process is a coherent process because যেটো induce কৰিছো আমি photon আৰু যেটো photon ওলাই যাব because of the coming down of the excited atom to the ground state, those two photons are coherent in nature. Okay, so this whole process of forced emission of photons which is caused by the incident photon is called stimulated emission, and this stimulated emission is coherent in nature with the stimulating incident radiation. So here suppose E1 is a lower energy state or ground energy level and E2 is an excited or an upper excited state level. Okay, so here N1 is the number of particles in the ground energy state E1 and N2 is the number of particles in the excited state E2. So normally in general N1 is always greater than N2, that is the number of particles in the ground level state is always higher than the number of particles found in the excited state. But there are some processes through which we can invert it. What we can do is we can make the population at the upper excited state more than the population in the lower excited state. There are some processes through which we can do it artificially. And if we can make N2 greater than N1, that is we can increase the number of particles more than the higher energy level than the number of particles in the lower energy level, then it is called population inversion. This whole process will be called population inversion, and the medium in which this process population inversion is achieved is always known as the active medium. And the method of raising the particles from the lower energy state to the higher energy state is known as pumping. The process of raising the particles from lower energy state to higher energy state is called pumping. And population inversion can be achieved by exciting the medium by suitable form of energy, and the process is called pumping. So there are various methods of pumping, like there is optical pumping, there is electric discharge, there is inelastic atom-atom collision, there is direct conversion, chemical conversion, etc. The term laser stands for light amplification by stimulated emission of radiation. So to understand the production of laser, we will need to understand what is spontaneous and stimulated emission, which we have already discussed. We have also discussed what is population inversion, and here we will see what is a pumping action. So how the laser operates, what is the working principle of a laser. So these are the main components of a laser. We need these three things to for working of a laser. Okay, first of all we need an active medium having metastable states. We need a resonant cavity, which is a specially designed cylindrical tube in which the light intensity can build up by multiple reflections. The ends of the tubes are silvered, and one end is completely silvered and the other end is partially silvered, so that an intense beam can emerge out of it. The third is a pumping system, which is required to achieve the population inversion. So what happens here, suppose here I have taken three energy state, E1, E2 and E3. E1 is the ground state, E2 is a normal excited state, and E3 is a metastable state. Okay, so now the lifetime of metastable state, as we have studied earlier, is 10 to the power minus 3 second. Mane atoms bur ba molecules bur particles bur metastable state etat kiman homoy kane thakibo pare 10 to the power minus 3 seconds. and the lifetime of a normal excited state is 10 to the power minus 8 seconds. মানে particles বোৰ at a normal excited state of 10 to the power minus 8 seconds থাকিব পাৰে. It is their lifetime. Okay, so now with suitable pumping method, some energy is supplied to the active medium, and because of that the atoms makes transition from level 1 to level 2. You can also show it with an arrow. The atoms emerges from, jumps from level 1 E1 to E2. Okay, the atoms in the E2, the normal excited state, stays for a short duration of time, 10 to the power minus 8 seconds, which is a very short duration of time, and then they immediately relaxes down to the intermediate energy state, which is E3, which is the metastable state, and they stays there for a longer, comparatively longer time, which is 10 to the power minus 3 seconds. On the other hand, what happens? The atoms are lifted to level 2, that is E2. The atoms are continuously lifted from E1 to E2, continuously. So the population of level 1 decreases and that of population of level 3 increases. E1 or population kini যেহেতু E2 লৈকে ই jump হৈ আছে, population খিনি E1 or কমি গৈ আছে, and because the atoms which are excited here are coming down to E3, so ইয়াৰ population, E3 population to বাঢ়ি গৈ আছে. So what is happening when the population of E1, which is the ground level, is decreasing, and the population of E3, which is an excited state as compared to the ground state, is increasing? What is happening? A population inversion, which is necessary for laser action, is achieved between E1 and E3. Population inversion, যেটো আমি পঢ়িছিলো, that excited state of population to ground state of ke besi hoi jay, hetu hol population inversion, that is achieved, which is required for laser action to take place. So now if an atom makes transition from E2 to E1 by spontaneous emission, by the process of spontaneous emission, by emitting a photon, that photon will again interact with the atoms of level 3, that is the atoms of E3, the metastable state, and it will force them to come down so that another photon is released in the same phase. Remember the spontaneous emission process ki hoy that at an atom, at an external atom, it will force that the particles of the metastable state to come down to the ground state, right? So further these photons will traverse through the active medium, যেটো active medium আছে তার এই photons will traverse over and they will compel the other photons to come down, and this process will keep on continuing unless the intense beam emerges out, and thus the laser action which is required is achieved, and the radiation which comes out is highly coherent, highly monochromatic, highly unidirectional, and that is the laser radiation which emerges out. The following are the most important properties of laser beam. Number 1, it is highly directional. Lasers emit radiations in a single direction. In case of ordinary light source, they radiates in every directions, in all directions, which is the difference is with its laser light. Which is the difference with the laser light, because it emits only in one direction, so it is highly directional. The next is it is highly intense. So intensity of light at any point is defined as the energy which is passing through unit area per second. So in case of laser, the spot size of laser is very small, so the whole energy is concentrated in a very small region, so it is highly intense. So it can pass through a surface, so it can penetrate through a surface because it has high energy, it is highly intense. Okay, so the third one is monochromacity. So it is the lasers are highly monochromatic. So monochromacity means it consists of a single wavelength, or you can say it consists of one color of light, which is not seen in normal ordinary light source. It is only seen in case of lasers. The fourth one is it is highly coherent. Coherence is the waves of light which are emitted, they have a constant relative phase. The waves which are emitted from lasers, they have a constant phase difference which is maintained, and it is due to the spontaneous emission of the lasers. Okay, so they are highly coherent, which give and due to the simulated radiations, the photons are emitted in the same phase, and the coherence of the laser beam, it makes it highly directional, highly intense, and highly monochromatic. So again, there are various applications of laser. So they are used in medical applications, like lasers are widely used in medicines. They've been used in treatment of retinas. They are also used in microsurgery because they are very focused. The laser lights are very focused, so they can be used in microsurgeries. They are also used for treatment of cancers in both human and animal. So their lasers are also used in communication applications. They are used in microwave communications, and because of their property of high directionality, laser beams are also used in communication between artificial satellites and moon. So lasers are also used in industries, like for example, they are used to blast holes in diamonds and hard steels, through which any ordinary photon cannot penetrate through diamonds and hard steels. So lasers are used because they have higher energy. They can penetrate through hard substances. They are also used in many scientific applications. You already know that, like it is used in certain reactions which is not possible in the presence of like ordinary photons. They are also used in research and various scientific works. The next chapter is fiber optics. So fiber optics is a technology which is related to transportation of optical energy through fibers, and fiber optical communication is based on the principle of light transmission through fibers by total internal reflection. So let us see what is total internal reflection. So when light passes from an optically denser medium to optically rarer medium, say for example from glass to air, then at the interface means this one, at the interface what happens, the light is reflected to the rarer medium. It is reflected away from the normal is this line, which is 90 degree to the interface. The incident ray of light traveling from the denser to the rarer medium reflects away from the normal. So as you will keep on increasing the incident angle means this angle, so what will happen, the reflection will be more and more. So at some point of time, for some specific angle which is known as, here you can see IC, this one is the critical angle. It is a corresponding specific angle for which the refracted ray will be 90 degree. It will be 90 degree. It will be like this. The refracted ray will keep on increasing, and at some point of time, at some specific angle, the refracted ray will pass exactly at the through the interface. So that angle, that specific angle is called critical angle. So how can you define critical angle? So the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree, that angle is known as critical angle. It is denoted by IC. So now if we keep on increasing the incident angle, and if we increase the critical angle more than the if we increase the incident angle more than the critical angle, then what will happen? Then the light, the refracted light will reflect back into the denser medium itself. Okay, a refracted ray dal bahi bahi goi eta time কি হ'ব, ইনসিডেন্ট এংগলটো ইমান ডাঙৰ হৈ যাব, ক্ৰিটিকেল এংগলটো ডাঙৰ হৈ গ'লে সি 90 ডিগ্ৰী পাৰ হৈ আহি যিটো মিডিয়ামেৰে গৈছিলে সেই মিডিয়ামটোলে উভতি আহিব, and this whole phenomenon is known as total internal reflection. Okay, and the critical angle here written as theta c is equal to sine inverse of 1 by mu, where mu is the refractive index of the medium. Here I am showing you the basic structure of an optical fiber. Here you can see this one is the innermost region, which is the light guiding portion. Here the light is guided through total internal reflection. So this region is known as the core. Then it is surrounded by another coaxial middle region, which is called known as the cladding. The refractive index of the cladding is always lesser than that of the refractive index of the core, which makes possible for the light to get confined to the core because it is required for the total internal reflection. And then you can see a layer which is known as the coating. Coating is basically a protective layer. There are two kinds of coatings. One is the primary and secondary coatings, which protects the entire fiber. That is, the coating protects the cladding and the core from any kind of external damage, like from abrasions, from contaminations, etc. The coating is present to increase the mechanical strength of the fiber and to protect the fiber. The acceptance angle of a fiber is defined as theta naught. It is denoted as theta naught. It is equal to sine inverse of root over mu1 square minus mu2 square, where mu1 is refractive index of the core of the fiber, mu2 is the refractive index of the cladding of the fiber. Okay, so the acceptance angle is the maximum angle that a ray of light can have relative to the axis of the fiber and propagate down the fiber. So there is another thing which is known as numerical aperture. The numerical aperture is this sine of the acceptance angle. So you can write sine theta naught. Theta naught is the acceptance angle. So sine of theta naught is nothing but mu1 root over mu1 square minus mu2 square. So numerical aperture can also be denoted like this in terms of refractive index. So numerical aperture determines the light gathering ability of an optical fiber. It is a measure of the amount of light that can be launched into the fiber. So here I have shown a basic block diagram of the fiber optic communication system. The fiber optic communication system has three major components, namely a transmitter, an optical fiber, that is the channel, and a receiver. So the transmitter, it converts the electrical signal to light signals. It consists of a source of light which is supported by the necessary circuits like the modulator, the carrier, okay, and the term channel here, it refers to the medium through which the message will travel from the transmitter to the receiver. So here the channel will be obviously in optical fiber communication system. An optical fiber is the channel which transmits the required signal from the transmitter to the receiver. And the receiver, what it does is it reconverts the transmitted signal using proper method of demodulation. The receiver will convert the light signal into the corresponding required electrical signal, which are then amplified and decoded to obtain the required message. So the optical fiber communication had many advantages over conducting wires because it has larger bandwidth, it is capable of handling a large number of channels, and it can travel very long distances, and it is also very fast. So these are the advantages of fiber optic communication system.